Number 9 on 401. Number 9 on 401. Again, this whole chapter's sort of been the same thing. A little difference in each problem. Number 9. I think they want you to do all the stuff up here. So we'll just go through and do it all. You might have to have out your stuff so you can help me with the formula. But I'll have it up here. Same, what we're going to do today, this is with proportions. Same idea, stuff that we're going to do today, only today's with variance and standard deviations. Number 9 says a medical researcher says that less than 25% of U.S. adults are smokers. So right away, before I go any farther, HOHA. It says less than 25% of U.S. adults are smokers. Is that going to be our HO or our HA? HA. And we're doing the P, so it's going to be P is less than 0.25.
That's your claim.
That's our claim. Make sure we write that in each time. What's that make our HO?
P is greater than or equal to 0.25.
So that's, again, on the test that you'll probably have next week. That's a start. In a random sample of 200, I'm just going to write some of these numbers up here. So N is 200. 18.5% said that they are smokers. So our P hat is 0.185. And our alpha this time is 0.05. Is there enough evidence to reject the researcher's claim? So we have our HO, we have our HA. Got to remember which part we're on now. Next thing we do, we start to draw our little graph. Our graph today is going to be different. Everything we've done in this chapter up to this point has been the normal curve, the bell curve. What we're going to do today is go back to the chi-squared curve, and we'll talk about that as we go. How do we know whether we're right-tailed, left-tailed, or two-tailed?
It's on the chart. And,
So what's this tell us? Left-tailed. So we're going to be over here. And we're going to use our chart. We're going to use this little chart. We got 200, so we're doing a z-test. On the little chart, our alpha is 0.05. We are left-tailed.
negative 1.645.
That goes there. We got 0 here in the middle somewhere. Then we're going to find our test statistic, which the formula for this one is P hat minus P over, it's like the square root of P times Q divided by N or something like that. Is that about right?
Yeah, that's it.
Have your calculators out so we can figure this out. P hat is 0.185. Big P is 0.25. That comes from the claim. Big P again is 0.25 times. If P is 0.25, what's Q? 0.75, good. And N this time is 200. Figure all that out for us. I would highly suggest that you're punching this into your calculator right now to see if you're getting the same answer as everybody else. Because this is probably the hardest one to punch in.
I got negative 0.471.
Wait. Hold on.
I'm writing them up there just to see if, till we get 2 or 3 or 4 people get the same answer. Then I hope that that one's right. Anybody else get that answer or something different? Everybody else too scared?
Hold on, I'm still trying to get it.
Think Isaac's gonna punch you or something if his answer's wrong?
What did he get?
Negative .471.
That's not what I got.
Well, what'd you get?
Negative 2.1241.
1, 2, what?
42.
4, 2?
No, 1, 2, 4, 2.
1, 2, 4, 2. Cody, you see me not doing this, right? Because you guys gotta know if you're punching it into the calculator, right?
I got
'Cause-
the negative 2 one.
Got this one?
Yeah.
I got that, but slightly different.
A little different?
A little different. 2.122.
Pretty close.
Oh wait, I got
Yeah.
2.122. Not the, yeah,
Yeah.
so if you're counting that then.
I did it wrong, it's that one.
Is this one?
2.1.
Yeah, I did it.
Yeah.
So everybody make sure that you know how to punch it into your calculator, otherwise come test time.
I tried to plug it all in my calculator at once.
Yeah, and this is the one I said, probably do the top first, do the bottom, then do the division, otherwise you're probably gonna get messed up. So 2.12, something like that.
It does not.
Where does that fall? Does it fall in the shaded or the not shaded?
It falls in the shade.
Shaded.
It falls in the shaded, falls over here somewhere. So what's that tell us? Reject the,
No,
No.
hypothesis.
alright? So again, this is on the test. 3 points for these things. Get this, your graph, that's another couple points. Your Z here, that's another point. Another point for deciding whether to reject or fail to reject. And then the final points come from, we say, our interpretation here with 5% level of significance. Is probably the only time today I'm gonna write this out, so make sure that you understand how to write these out. With 5% level significance, that's the first part. Then we go to this chart. Our claim was our HA. So we're looking at this column, and we rejected the null, so we're looking at this top box right here. 5% level significance, there is enough evidence to support the claim. And that's our first 2 parts, then our last part is to tie it to the problem. Of the researcher
Don't smoke a cigarette.
that less than 25% of US adults are smokers. The test probably won't be real long. I can't remember exactly how long it is, but probably like 5 or 6 problems. That's one problem. Can handle all that. What we're going to cover today: hypothesis testing, so still testing. but now we're gonna do variance and standard deviation. Remember variance? Sigma squared, if I could draw sigma, and standard deviation. Standard deviation is just sigma. So sigma squared or s squared and sigma and just s. So we're going to find the critical values. This is the one that everybody apparently didn't remember on that last symbols test. Chi-squared. So we're going to do a chi-square test. It means we're going to use a different chart on all your stuff. In real life, where this stuff is used, and this is probably used more than any of the other stuff that we've done this chapter, even though the testing isn't as good as for mean and proportion, this is probably used more. In real life, it's important to produce consistent results. So if you own a business or something and you're making something and you're putting it out there all the time, it should be consistent. Example, golf balls. If we're putting out golf balls and you're selling these high dollar golf balls, they should all be the same size, same weight, same density, everything should be the same. And we can check out to make sure that all of them are coming out the same by using what we're going to learn today. A bag of chips, there's rules that the government puts on bag of chips, candy bars, whatever it is, that they put on them to say, hey, it has to be within this range. So when you get a bag of chips, you think, oh, there ain't no chips in here. Well, that can't be true because otherwise the company would get in trouble for not having the chips in it. Anybody know with a bag of chips, why is there so much air in a bag of chips?
Are you looking forward?
Nope.
So they don't get squished.
For
So
the
they don't
weight?
get smashed.
Oh,
Doesn't have anything to do with
well, it's
them,
grip off.
them trying to cheat you,
That's why
and that's what everybody thinks.
Is more full because they can't.
Alright? The whole purpose of putting air and making the bag look bigger like that is so that as the chips are getting packed in the box and shipped around everywhere, that they don't get crushed. Car parts, go to AutoZone, you buy a car part, you hope that that car part actually fits what you want it to fit, otherwise you're wasting your time. They're not gonna call you or anything?
I bought
They did
car
it
paint
last
one
time.
time.
Huh? You what?
I had to buy car paint one time. I scratched my
Scratch
car.
everywhere.
But guess what? George still don't know.
I'm gonna tell you.
You can't even tell. The people were kind of rude there. I didn't.
I'm gonna send out a special email with
Oh,
you.
crap.
George, that was your daughter talking. She scratched her car at some point. Go
It was
figure it out.
a little scratch. But it worked. I still have the pin in my car.
Did you get your car stuck on
Did you say
the
my
drain?
screws are like crap?
You got your car stuck where, Jenna?
Like a man.
You got stuck on a drain?
Yeah, back out there by the softball field. That big
And
rain
one time
hit.
she hit Olive Garden, didn't you?
She ran into a building too?
Yes.
No, I didn't. Oh, Granny had the little. I had the curb.
In the driveway.
No, I had the curb with all the rocks.
Yeah.
That one was bad.
That, I don't have George's email, I have Mom's, so.
Well, it's alright. It's a better driver than she is. I'm on rides and brakes.
Alright, finding critical values for the chi-square test. I wouldn't write any of this down, this is just what we're gonna do. Specify the level of significance, so you're gonna find your alpha, your degrees of freedom, you gotta find it. The harder part for this one, this right here is gonna be different than everything else we've done this chapter, so you really gotta watch closely on this one. You gotta decide whether it's right-tailed, left-tailed, two-tailed, but then the way we find the stuff is different. If it's left-tailed, so with our chi-square, remember that graph's gonna look like this, it doesn't look like the normal curve. If it's left-tailed, over here, you gotta do 1 minus alpha, then use the chart. If it's right-tailed, you just use the chart, and it tells you. If it's two-tailed, then you gotta do half alpha, or take alpha and divide it by 2. And that's gonna tell you your, right tail. And then you're gonna take that answer and subtract it from 1, and that'll tell you your left tail. And we'll do more of this, I'll show you here in a minute on the other slides. But each one's a little different, so you got to watch what you're doing with these chi-squares. So with right tail, and this I'll write some stuff down here. You might write this down. With a right tail, you just use the chart. Left tail, you do 1 minus alpha, then use the chart. And when it's two-tailed, we do this. You take alpha divided by 2, that's going to give you one of your numbers, and then you subtract that number from 1, and that's going to give you your other. And you use those two on the chart. So put those, do both of them, and that's going to tell you 2 numbers separately. And we'll do a problem or 2 here to help you make sure you understand it. How about your charts so we can do them? So find the critical value for a left tail. If n is 11 and alpha is 0.01. So if n is 11, what's our degrees of freedom going to be?
10.
So that's 10. And we're going to use the chi-square chart. So make sure you can find the chi-square chart in your charts there. Mine's probably in a different spot than yours. So the chi-square chart is here. And on this one, remember, we're not a normal curve this time. We're doing left tailed, so that's over here. Right tailed is just normal. You just use the DF and the alpha,
You don't even know.
and it's going to tell you the number. Left tailed, what you got to do first is you got to take 1 minus that. So 1 minus 0.01, which is 0.99. And we use these 2 numbers in the chart. So 10 and 0.99.
2.558.
Now, is that supposed to be a negative because it's over here on the left?
No.
No, remember with chi-squared, everything is positive. So if we were doing the z-scores or whatever, then that would be a negative if we're on the left. But for chi-squared, that's a positive. So that's our critical value. Hopefully we did it right. 2.558. So this is our rejection region. Everything else is basically going to be the same. We're going to do the same setup. Again, finding the chi-squared, the test statistic is going to be a little different to see what goes in here, and whether we reject or fail to reject, that formula is different, but otherwise it's doing the same stuff. Find critical values for a two-tail. This one's a little harder. Again, DF. What's DF if our N is 9? Now for our two-tailed, what we have to do, we're looking for this one, we're looking for this one. First thing we do is we take our alpha and we divide it by 2. Somebody help me out, what's 0.05 divided by 2?
0.025.
That's one of our answers.
41.
The other one, you just take that answer and subtract from 1. So 1 minus 0.025, what's that give us?
Oops.
0.975. We're going to use these two numbers, our DF, Look them up on the chart, and those are gonna be our two critical values that go in these two spots.
The 0.975 is 2.180. And then, what is the other one?
How do I know that that one went over here? Because as soon as you find the other one,
Smaller.
it's gonna, the other one's gonna be bigger than that.
15.507.
Everybody see those on the chart? And then these are our two rejection regions. If our test statistic falls in one of those two regions, then we reject the null, and so on and so on. So nothing really hard about this, you just gotta remember it's a little different than the others. So we got 0.025 and 0.975, we did that right. See if we got these two numbers right. 2.180 and try this one again.
You were over by one.
Oh,
Were you one number off in the,
yeah, I didn't go over one. It's 17.535.
trying to make me look stupid on my video. Chi-square test. So again, your chi-square test is for variance, standard deviation. I wouldn't write any of this down. Statistical test for variance, standard deviation, this is just telling you what it is. Can be used when the population is normal. The population has to be normal, no ifs, ands, or buts. If it's not, if the population's not normal, we can't do this. Your test statistic is your S squared or your S. So it's either your sample variance or your sample standard deviation. This formula, this I would write down. This is the formula that we're going to use to find your test statistic. This one's not very difficult. I will have you write down something else along with this formula here in a second, though. You've got to remember with this formula, if you're doing variance, then the formula tells you exactly what you're doing. All right? If you're doing standard deviation, you've got to remember to square this number and that number. So if it's variance, they're going to tell you what S squared is and what sigma squared is. But if it's standard deviation, they're just going to tell you S and sigma, and then you got to remember in your calculations to square the two. So variance one way, standard deviation another way. I'm going to put all this up here, then I'm going to write something down here. These are your steps to do this. Nothing hard, except for on this one. On this one, remember, left-tailed, right-tailed, or two-tailed. You got to know the different ways for each one. So if it's left-tailed, it's one thing. If it's right-tailed, you just use the chart. If it's left-tailed, you do 1 minus alpha. If it's two-tailed, you got to do alpha divided by 2, and then subtract that answer from 1. you can read any of that or not. So if it's right-tailed, you just use the chart. If it's left-tailed, you do 1 minus alpha, then use the chart. If it's two-tailed, you do alpha divided by 2, and then that answer subtracted from 1, and use those two numbers in the chart. Basically, everything else is the same as everything we've been doing all chapter. You state the HO and the HA, figure out what your alpha is, your level of significance. This time you have to find your degrees of freedom. One of the other times in this chapter we had to find the degrees of freedom. Then you start to draw your picture. This time we're drawing the chi-square instead of the normal curve or the bell curve. Then the other steps are basically the same as the rest of them. Number 5, just drawing your picture. Number 6, you're finding your test statistics using that chart. Number 7, you decide whether to reject or fail to reject the null. And then number 8, you interpret it. And again, that's going to be using that other chart. When you draw this time, remember you're not drawing the bell curve, you're drawing the chi-square curve. All right, on this problem, it says dairy processing company claims that the variance of the amount of fat and whole milk processed by the company is no more than 0.25. You suspect that this is wrong and find a random sample of 41 containers. Has a variance of 0.27 at a level significance of 0.05 or 5%. Is there enough evidence to reject the company's claim? Assume that the population is normally distributed. First thing we're going to do on this, and I'm going to do some of this, just try to fit it in right here. We're going to find our HO and our HA. So this time the company's claim that the variance processed by this company is no more than 0.25. So it's variance. So it's going to be sigma squared. And the company's claim, it says no more than. Is that gonna be our HO or our HA? If it's no more than.
That's your HA. That's your,
What's no more than? Tell us which symbol.
less than, oh, it's your HO.
So that's your HO,
But that's your claim.
and that's your claim. Good. And then that means HA, or yeah, the HA has to be greater than 0.25. Then I always write down all my other numbers, so like this time we know N is 41. Well, if N is 41, our DF is 40. Our alpha is 0.05. Equals 0.05. And 0.27 is our S squared. That's our sample variance. So we need all those numbers. We're going to plug them into the formula and stuff to help us do all this. Our graph, and I'm not going to have space to draw a graph right here, but I'm just going to draw a little bit of it. Our graph's going to look something like this. This tells us that we are right-tailed. So if we're right-tailed, all we're going to do is use our chart and our alpha and our DF. So our DF is 40. We go down to 40 and go over to 0.05. What's that tell us? So that's what should go right here, 55.758. Hopefully that's right. I can't see it, so. So looks like we did that right. Our alpha, 0.05, our DF is 40. We did all that right. Our rejection region should be right-tailed with that 55 point whatever on it, 55.758. Then our test statistic. The formula for our test statistic this time is chi-squared equals, what was it? It was n minus 1 times s squared over sigma squared, right? Is that the right formula? N was 41, so that's just going to be 41 minus 1 is 40 times s squared. They already squared this for you this time. And I think it was, no, I don't want to do that. What was it, like 0.27, I think, wasn't it? And their claim was 0.25. So we're just going to plug that in. Now this is a lot easier this time, especially if you do the n minus 1 in your head. Because all you're going to do is multiply these two together, then hit divided by 0.25, and that should give you your answer. So it's 40 times 0.27 and then divided by 0.25.
43.2.
Let's see if that's right. Yep. Then we just see where that falls at. Looks like it falls somewhere about in there. And that tells us to fail to reject the null. And then once we fail to reject the null, we're going to say with a 5% level of significance, there is, we go to the other chart in here. Our claim was our HO. We failed to reject, so we're here. With the 5% level of significance, there is not enough evidence to reject the claim that, and their claim, the company's claim was that their milk contains less than or no more than 0.25 of, what was it, fat? Yeah, amount of fat in the whole milk is no more than 0.25. Same stuff, doing the same stuff, been doing all chapter long, just now with the chi-squared stuff. And again, on this one, these two, we didn't have to square them because they were already squared because we were dealing with variance. On some of them, you'll have to square those. And I think this is one of them. Yep. The companies claim that the standard deviation of the lengths of time it takes an incoming telephone call to be transferred to the correct office is less than 1.4 minutes. A random sample of 25 incoming telephone calls has a standard deviation of 1.1 minutes. At a 10% level of significance, is there enough evidence to support the company's claim? Assume the population is normally distributed. So again, first thing we're gonna do, HOHA. Their claim this time, transferred to the correct is less than 1.4. So if it's just less than 1.4, that's gonna be our HA. And this time we're dealing with, let's see, standard deviation. So that's gonna be our just sigma, not sigma squared, less than 1.4. That's our claim. That means our HO, our null hypothesis, is greater than or equal to 1.4. This number this time, instead of me writing them all out up here because I don't have enough space, this is our sigma. This is our S. Of course, this is our alpha. 25 is our N. That means our degrees of freedom is 24. And that should be all the numbers that we need. This time we look right here, that tells us that on our little graph, we're going to be left-tailed, so we're going to be over here. We wrote our HO and HA, looks like we did that right. Alpha is 0.10, DF is 24. To find our rejection region, go back on our chart, our DF is 24, our alpha is 10. Remember this time, to find that rejection region, since we're left-tailed, we gotta do 1 minus 0.0 or 0.10. So that's 0.90, so we're using 0.90 and 24 on the chart. It's in the dark space again, so I sure can't read it. Somebody help me out. 24 and 0.90.
15.659.
That what we had last time? Is that something different? So 15.659, that's our rejection region. Then we do our test statistic. Our chi-squared is going to be n minus 1, which is 24, times our S, which was 1.1, over our sigma, which is 1.4. But we got to remember this time that each of those needs to be squared. So since this was standard deviation, you have to make sure that you remember to square each one of those. And again, you should be able to type this into your calculator just like this: 24 times 1.1 squared equals, and then divided by 1.4 squared and hit equals. Somebody help me out, what's that give us? then we check that and it falls somewhere about right in there. So what's that tell us to do?
Failed to reject.
Which one is it?
It's failed to reject, it's in the shade here.
It's in the shaded, that tells us to
Oh.
reject, right?
Yeah, exactly.
So we reject the null. Then our statement's gonna be at a 10% level of significance. There's enough evidence to support, again, you have to go back to this chart to find that, to support the claim that the standard deviation of lengths of times it takes an incoming telephone call to be transferred to the correct office is less than 1.4 minutes. Last one, sporting goods manufacturer claims that the variance of the strengths of certain fishing line is 15.9. A random sample of 15 fishing line spools has a variance of 21.8. At a 5% level of significance, is there enough evidence to reject the manufacturer's claim? Assume the population is normally distributed. So again, we do our HO, our HA. HO, HA. The claim is variance of a strengths of a fishing line is 15.9. Well, is tells us equals. So, and it's variance. So that's gonna be right here. Gonna be sigma squared equals 15.9. That's the claim. Our HA then is gonna be sigma squared does not equal 15.9. That tells us that we are two-tailed. So when we go to draw a little graph, we'll have a tail here and a tail here. Have two rejection regions. And that's gonna change the way that we find everything on our chart. Let's see, 21.8 is the sample, and there was N is 15. So that means DF is gonna be 14. This is our our S squared, 0.05. Did the HO and HA right, that looks right. 0.05 is our alpha, our DF is 15 minus 1, which is 14. So when we draw our rejection region, if it's two-tailed, it's a little harder, but not really all that real difficult. If it's two-tailed, you do alpha divided by 2, so 0.05 divided by 2, which is 0.025. I think we already did this one. Then you subtract that from 1, and you do 0.9725. So we use our DF and these two numbers. Look up on the chart to find our rejection regions. So 14 and 0.025. Again, 14 is in the dark. 14 and 0.025 looks like 26.119. And then 14 and 0.975 looks like 5.629. So those should be our two rejection regions here, our two critical values. Then the test statistic, this time it's sigma squared, so we don't have to square each number. It's going to be n minus 1, which is just 14 times s squared. Well, s squared was, I don't remember what s squared was. What was it, 21.8 or something like that, I think. Divided by sigma squared, which is 15 point, and we don't square that, because it's already squared. Divided by 15.9. Somebody help me out there, what's 14 times 21.8? divided by 15.9.
98.19.
That way it's in. And then we check, see where that falls. It falls somewhere about in there. So what's that tell us? Fail to reject. So we fail to reject it. If we fail to reject it, then again, it's gonna say with a 5% level significance, we go to our chart. Our claim was our HO, and we failed to reject, so we're down here with a 5% level significance. There is not enough evidence to reject the claim that the strength of the fishing line is equal to 15.9, whatever the units were. I don't remember what it was. I guess it didn't give units. It just says strength of the fishing line is 15.9. This is your assignment. Again, next class we'll probably review, because I think this is the last section in this chapter.